So if you've got 25 centimeters of a basic solution and it reacts with 50 centimeters cubed of an acid solution, what is the molarity of the acid? Before you can do anything, you've got to actually write a balanced equation. And this is possibly the easiest of all the balanced equations to write. So, I mean, it's not because, sorry, that's a capital N and a lowercase a, OH. This is not great. And then you get H2O and NaCl, and it's a complete 1-to-1 ratio, so there's nothing difficult in it, but you are expected to do that because it's not always a 1-to-1 ratio. So you're going to go Na over Nb is equal to Ca Va over Cb Vb. You don't have to do it like this. You can go the longer route, which is probably more authentic, but this is quick and easy, especially in a quick and easy example. And you've got the concentration of the acid that you're looking for. You've got the volume of the acid. It's centimeters cubed, and good news, the volume of the base is in the same unit, so it all stays the same. And I've got the concentration of the base, so I put that into a bracket over there, and when I rearrange that all, I land up with the concentration of the acid turns out to be 0,05 molar. Then you've got 25 centimeters cubed of a certain solution of sodium hydroxide, and it's the same balanced equation, so that's good news. So I've still got a 1-to-1 ratio, and again, as simple as this, I go 1 is to 1. I've got 25 centimeters cubed. I've been given a volume of base, and I've been given a concentration of base, and I have been given a volume of acid, and I'm expected again to find the concentration of the acid, and when I rearrange that particular one, I land up with 0,092 moles per cubic decimeter for the concentration of the acid. On to the next one, we've got 25 centimeters cubed of sodium hydroxide, and we're using that same balanced equation again. So it's a 1-to-1 ratio, which is pretty simple. And again, Na over Nb is equal to Ca Va over Cb Vb. And that's going to be 1 over 1. And concentration of the acid is given to me 0,1. I am told the volume of the base is 25, and it reacts. I've been given the volume of the acid at 15, and I'm expected to find the concentration of the base, and the concentration of the base in this case turns out to be 0,06 moles per cubic decimeter. Then we've got succinic acid, and it has this formula, but there's a little problem with the formula, and that is this N over here, and it reacts with dilute sodium hydroxide as follows. Good news is that it is a 1-to-1 ratio in terms of the way that it, oh no, it's not, it's a 1-to-2 ratio, so keep an eye on that. And then I'm given a number of grams of the acid that's dissolved in water. So this is a whole lot more complicated than the standard stuff that we've been dealing with up until now. So the first thing I'm going to have to do is I'm going to work out my number of moles of acid is 1, number of moles of base is 2. I am given that the solution was placed in a burette, so my volume of acid is 18,4, and I needed 25 centimeters cubed of base, and the concentration of that base was given. So I'm going to work out the concentration of the acid first. And I found out that my acid is actually 0,068, for want of a better word, moles per cubic decimeter. Keep that whole thing in your calculator. And now I'm going to say, well, how many moles is that? So number of moles is equal to concentration times volume, and I've got 250 centimeters cubed in having made that up. So it's the 0,068 multiplied by, remember I've got to change this into decimeters, 0,25, and I get a number of moles. And it is 0,017 moles. And then I have got a mass. So molar mass is equal to mass over number of moles, so it's going to be 2 divided by 0,017, and I land up with 117,76 as the molar mass, so it's grams per mole. Now I need to look at this particular equation, and I can see I've got a CH2, a COOH2. So I'm going to work out all of the number of moles is over here. So it's carbon plus oxygen plus, I'm looking at the second half, plus hydrogen, and that's all multiplied by 2, which is going to be equal to 90, and therefore I can chop 90 off this 117 and see what we get to, and we're left with 27,76. That could be CH2. CH2 is 12 plus 1 plus 1, so it's going to be 14. So I'm going to divide this 27 by 14, and for all intents and purposes, that's going to land up being 28 divided by 14, and this little 2 over here turns out to be 2. Sorry, that little n over there turns out to be 2. So I've had to work all the way backwards. I first needed to determine a concentration. From the concentration, I got the number of moles. From the number of moles, I got the molar mass. I could then remove the parts of the molar mass that I did know and finally come up with the little bit that was unknown. So once again, you've got this concept where you've got a mass to make up a standard solution. You don't know the molar mass, but you're given a titration equation to be able to work out a concentration. So it's number of moles of acid over number of moles of base, concentration of acid, volume of acid, concentration of base, volume of base. So it's 2 over 1 is equal to concentration of the acid, 0,1, the volume of the acid, 24,5. The volume concentration of the base is unknown, the volume of the base is known, and I land up with a concentration of base which is equal to 0,049 moles per cubic decimeter. You're now going to say, I know the concentration and I know the volume, so I can work out from there how many moles I've got. So I'm going to say number of moles is equal to concentration times volume, 0,049 multiplied, and in this case I must change that 250 into 0,25 because I need to be compatible with the unit moles per cubic decimeter. So this is moles per cubic decimeter. In the other one, you may think, why didn't I have to do it here? Because these are centimeters cubed, which cancel with centimeters cubed, so it's not a compatibility issue, whilst in the second part here it is a compatibility issue. So you're going to land up with 0,01225 moles. Now, I have a mass and I've got a number of moles. I can work out a molar mass. Molar mass is going to be equal to mass over number of moles, 3,5 divided by 0,01225. And I get an answer of 285,7 grams per mole. Now we need to see what part did I know. I already knew the sodium carbonate aspect of it. So what's the molar mass of sodium carbonate? It's going to be 23 plus 23 plus 12 plus 3 times 16, and that turns out to be 106. So I just take that 106 away from the 285 that I had, and I'm left with 179,71, which for all intents and purposes is about 180. And then I say, all right, well, I know water. I don't know how many waters I've got, but I know that water is 18. 16 plus 1 plus 1. So I'm going to divide this by 18, and I land up with 10. Then the next one, we've got a 25-gram sample of vinegar, and it's pipetted into a volumetric flask, and I get 250 centimeters cubed. The solution is placed in a burette, and that's how much is required to neutralize that. Calculate the molarity of the original vinegar solution. So now we're going to be doing something with dilutions as well, so let's work through that. So first things first, we are going to have to work out our balanced chemical equation, and we have got vinegar, which is COOH, and sodium hydroxide, and you should know from your organic chemistry last year, that this acid only loses 1 hydrogen. So it's going to become water plus sodium acetate. The acetate ion is CH3COO. So that's sodium acetate and water. So it is a 1-to-1 ratio, which is quite good news because that does make my life a little bit easier. Number of moles of acid, number of moles of base is equal to concentration of acid, volume of acid, concentration of base, volume of base. 1 is to 1. My concentration of my acid is what I do not know. My volume of acid is 13,9. My volume and concentration of base is given there, 25 and 0,1. And I'm going to land up with a 0,18 molar solution of acid. Now with that, I know that I have made that up to 250 centimeters cubed. How many moles did I originally have in the 25 centimeters cubed? So we're going to go as follows. First, I'm going to work out my number of moles, and my number of moles is equal to concentration times volume. I've got a concentration of 0,18, and I've got a volume of 0,25. I've had to change that 250 centimeters cubed over there into 0,25 in order to establish my concentration, and I land up with 0,045 moles. That came out of 25 centimeters cubed. So if I go back to my little container system that I've shown you before, in my big container I have got 0,045 moles. Oh, that doesn't look very good. And I have got a volume, so that's my number of moles. My volume is 250 centimeters cubed, and my concentration was 0,18. However, here I have got that many moles that came from a dilution of 0,045 moles. I don't know the volume, sorry, I do know the volume is 25 centimeters cubed. And finally, I have got a concentration that I am attempting to calculate. And when I take the concentration is equal to number of moles divided by volume, which is going to be equal to 0,045 divided by 0,025, I land up with a concentration that is equal to 1,8 moles per cubic decimeter. Now remember, let's just remind ourselves what we were looking for over here. We had 25 centimeters cubed of a certain sample that was put into a volumetric flask and diluted up to that volume. A certain amount, 13,9 centimeters cubed of that stuff, then got used in a titration, and I was able to find out the volume and mole ratio over there. But it's a dilution first, and from the dilution I'll get my number of moles. From a number of moles I can do a titration. But I didn't know the dilution, so I went the other way. I knew the titration, I could get the number of moles. From the number of moles I can do a dilution calculation.